Welcome to Math 119, Chapter 1.2, where we're talking about properties of exponents and radicals. Now, for those that are taking the class in person, we do a lot of this section throughout our entire 119 journey. So you'll hear me reference this chapter quite frequently. So make sure that you have these skills down quite well before moving on to the other chapters and sections. All right, so natural numbers and integer exponents. So it says if a is any real number and if n is any natural number, then a to the n can be written as a multiplied by itself n amount of times. So that we can kind of break this down, a is going to be considered your base, and n is going to be considered your exponent. The number of times that you want to multiply a. Number of times we multiply a. So for example, if we had a to the fifth, we're going to be writing a multiplied by itself 5 different times. 1, 2, 3, 4, 5, and there you go. Kind of different from a coefficient where we're going to be adding the same amount of a variable, right? So adding, we have a coefficient. For multiplying, we have the exponent there. So let's see if you can pause the videos and do some quick examples. So 2 to the fifth, if we don't know it at the top of our head, which I'm hoping by the end of this class, that something like this does not phase you in the slightest. So in case right now we still have to kind of write it out, right? 2 to the fifth is just writing 2 5 different times. And then we can slowly break it down. We have 4, we have another 4, we have 16 times 2. So we actually end up having 32. So from now on, if you see 2 to the fifth, it's really going to be 32. Let's do it again. 3 written out, 4 times. 3 times 3 is 9. Do it in a different color. And another 3 times 3 is another 9. 9 times 9 is 81. Doing it again, 4 to the thirds. 4 times 4 times 4. So we have 16 times another 4 for 64. And one last one. 5 times 5. 25 times another 5 for 125. Now, if you're in my class, you do not have to write out these steps for me unless it is helpful for you when going to show your work. So if we're going through and you see something like this on a homework, a quiz, a test, you just go right for it as long as you know the answer. Okay. So now let's move on to what we do with variables. So if we have x to the third power times x to the fourth power, right? What do you think we're actually going to do? Well, down below, right, it tells us that if a to the n with the same base is being multiplied by a to the m, right? We're just writing out these amount of factors, right? This is really x times x times x times another 4 x's. So how many x's do you have in total? Well, we have x to the 7 in total. The quickest way to do that and recognize the relationship between 3, 4, and 7 is that we are going to be adding those exponents together. So when you see any sort of multiplication, x to the third times the same exact variable with an exponent, we just get to add those variables together. This kind of allows us to skip the whole step of writing all of these x values out. So to kind of give you an advantage, if multiplying with same base, we add the exponents. We're going to be seeing lots of rules today, which we do have a very generalized rule. I believe it's on our next page. So let's try it again with B and C. So notice that we won't have variables this time around, but let's see if you can challenge yourself with B and C. Now the main idea or the main difference between B and C is that one of them has an exponent, or one of them has a parentheses and the other doesn't. So now this B can be written as -1 times 3 to the third. That negative is not directly attached to the 3. You can represent it as having a -1. And then we can multiply out 3 to the third. 3 times 3 times 3 for -27. So if you don't have parentheses, most likely, actually, if you don't have parentheses, that negative is going to remain. Whereas on one like C, it has the potential to lose the negative. So when we write out something like this, -2 all raised to the third power, well, we're just going to copy what we have written, parentheses and all, 3 different times, or however many times that it's required. In which case, right, 2 negatives make a positive. So these ones will cancel out the negative to give you a +4 multiplied by, again, a -2. So we have a -8. If this was different, if we had it to the 4th power, then we would, again, multiply this -8 with a -2 to then have a +16. So C with your parentheses has the potential to drop the negative, and B without any sort of parentheses will have that negative remain. Now the last one, D, is kind of similar to A, but just thinking about it in the reverse order, right? So the opposite of multiplication is division. So the opposite of addition is subtraction, right? So if we wanted to show it that way, we could say 7 to the 6th minus 4, which is equal to 2. So 7 squared, which is 49. Now let's say you're not ready for that. Just like we did at the very beginning, we can write out however many 7s that we have. So we should have 6 on top and 4 below. Now, because you have the same exact thing below as you do above, we can actually go ahead and cancel. So we can cancel 1 for 1. And what's left over is 2 7s. 2 7s being 49. Okay. Now, the reason why we end up subtracting will come in from our next rule. So before we get too far ahead to look at our next rule, think about what we have done just a moment ago when we had any sort of adding of the exponents, where you said, hey, we add the exponents when we end up multiplying the two values of the same equal base, right? So with that being said, what happens if we have a to the 0 power being multiplied a to the m power? Well, a to the 0, a lot of students at first glance think, okay, well, this is really 0 times a to the m, so it must be equal to 0. But it's actually not equal to 0. So instead, right, we said if they're being multiplied, right, we're really going to add the exponents. So we're going to add 0 plus m. So what is 0 plus m? Well, it's really just a to the m, right? So a to the m, which means what about a to the 0? If it didn't come out as being 0, what did it come out to be? Right? Well, it's really, so sorry, I meant to put 0. It's really a placeholder value. In order for this to be true, right? In order for this portion, I should say, to be true, a to the 0 must be equal to 1. Otherwise, if it's equal to 0, it's going to cancel everything out. If it's equal to any other number, so let's say if it's equal to 1, right? Well, a to the or I guess 2. So sorry, a to the 2, right? We're going to be adding 2 onto the m, or 1 onto the m, right? So a to the 1 in total, anything to the 0 power, is equal to 1. And I'm going to write that there somewhere. Anything to the 0 power is equal to 1. No matter what it is, it will be equal to 1. And you'll notice that as you're decreasing your exponent values, right, it goes from 27 to 9 to 3, and then to something. That something can't be 0 because there's no coming back from it. So instead, there's a placeholder value of 1. So if that's true, then what follows suit? Because these values are decreasing, right? They're getting smaller and smaller. So what is smaller than 1? Well, our next rule is going to suggest what we do. So if we have a to the negative n, then we can say that we can use the reciprocal rule. I'll write that here. So any sort of negative exponents, if you have it, we'll use the reciprocal property. We are going to flip it upside down. Now, when we go to flip, I'm actually going to say, because I hate the word flip with the students, because they think everything flips, when really it's only the value with the negative exponent that does the flipping or the switching. So you're going to hear me say a lot of the times, it's going to change its location. So that being said, changing its location, if this is really over something, right, over 1, then to reverse it, to change its location, if it's in the numerator, it will then come in the denominator. It's going to change its position, its location. And then it'll have a positive exponent. And I'm going to make it, that's right here. So with that being said, can we take a look at just the following examples from A, kind of that continuation. Again, what comes after this 1? So with that rule in mind, right, changing the position or the location, well, if 3 has a negative 1 as its exponent, to get rid of that negative portion of the exponent, we're going to change its location, right? Because there's no other values that are given, right? We're just going to have 3 over this 1. We're going to then change the location of the 3. It's found in the numerator. And so now we're going to place it into the denominator. 1 over 3 to the positive first power. Let's do it again. 1 over 3 squared, and it's positive 2, which means 1 over 9. And notice that we are going to be getting smaller and smaller with these fractions. Right, one more, 3 to the negative third. Now, if you haven't paused the video, I would definitely suggest pausing it now to give yourself some practice. 3 to the positive 3, which means 1 over 27. And last, 1 over 3 to the negative fourth. Again, changing its position. We're going to go from the denominator, we're going to move it into the numerator. 3 to the fourth power, which is 81. Now let's try out B and C. So pause the video, see what you can come up with first, and then when you are ready, just come back to this video. So first off, we have 2 to the fourth, x to the negative third power. So let's take a look at the exponent of your coefficient, right? 2 to the fourth is really 16x to the negative third power, right? Or even better, actually, let's say I reversed it. Maybe it's a little easier to see it this way, right? How do you get rid of that negative exponent to start? Right, well, we said change its position. Now notice that I'm going to just say change its position. Change only the exponent with the negative exponent. So that just means of these two, right? What's 2 to the fourth, right? What's its exponent, right? Well, your exponent is 4. Is it a positive 4 or is it a negative 4? Right? Well, this has a positive exponent, so we keep the position. Whereas this x, right, has a negative 3. This has a negative exponent. So when we go to change the location of the negative exponent, it's only the one with the negative that we switch around. A lot of the students who just say, oh yeah, we just flip it, end up coming up with the wrong answer because there's two different things going on. One that has a positive exponent and the other that doesn't. So when we go to change the location, we're really only interested in moving the x's position. So you have 2 to the fourth over x now to the positive 3, and then finishing it out. Because it is so important, only change the location of the let's see, of the, I'll say value. So with that being said, can you now try out C? So if you made a mistake, can you go back and fix it? Well, first, let's go ahead and switch those positions of those negatives. So y to the negative 6, that'll come down. And z to the negative 1, that'll come up. So you now have 5x. Z, we said, is now up here. Z to the positive 1 over y times now y to the negative, or positive 6. So sorry, it's now positive. Now, is there anything that we need to clean up? Just a little bit. 5xz can all remain. Then you still have y times y. So if they're found next to each other, they can actually be added together for y to the 7th. Okay, so now let's look at these properties all at once because we have seen a lot. So it's kind of a nice overview as to what we have done before. Now, this first one is called the product property. There we go. The product property, so we get to multiply these bases together, but as we're multiplying your bases together, we are actually doing what to your exponents? So we are adding your exponents. So add exponents. So for example, if we had x to the 5th times x squared, that will make 7. A lot of students, sometimes when they get started, they see that multiplication. Keep in mind, this is not equal to x to the 10th. Do not multiply. The product property is just where you see a multiplication symbol and you actually add their exponents. Now, if you can get the first one, then the next one is actually kind of goes hand in hand, right? The opposite of multiplication is division, right? We say quotient or quotient property, right? So the opposite of multiplication is division, which we can see here. The opposite of addition is then subtraction. So we're going to be subtracting the exponents. So for example, x to the 5th over x squared. So 5 over 2 or minus 2, which is equal to x to the 3rd. Most students get this one right away and don't typically make mistakes on it. All right, your next one is that negative rule or that reciprocal rule. It just means we are going to change the position of the exponent. Change position of the exponent. So if we had 5 to the negative 2, right, then we would drop that exponent, make it positive, and clean it up. The same goes for if you see it in the denominator, negative 3rd. So to raise up and then clean it up. Now, number 4 is called the power rule. Most students confuse number 4 and number 1, the product rule, with each other. And it makes sense. I understand why we do it. But just as best as you can, when you see a power being raised to another power. So this power is being raised to another one, right? What do you see happening with those exponents? Well, it might be hard to tell because this attachment is a little bit blurry, but we're going to be multiplying the exponents. This is when we can actually bring them together through multiplication. So for example, if we had x squared to the 5th, then we can go ahead and multiply 2 times 5 for x to the 10th. Pretty much if you see a pair of parentheses and another exponent, then you're going to be multiplying that in. Now 5 and 6 is the same type of rule. It just says, I want to just say it's like a distributive rule. Notice that A and B are no longer having the same bases as before. They're just 2 different bases. So that just means we get to distribute your exponent throughout, throughout the parentheses. Now, students who do end up having a mistake on this, let's say, for example, 2x to the 3rd. A lot of the students can recognize you will have x to the 3rd, but a lot of students just kind of leave it here and just say, oh yeah, I'm done. But make sure we are distributing throughout your parentheses. That 2 is still, it still matters. It's just representing that a out front, your coefficient. So really, we want to put 2 cubed, which is 8x to the 3rd. This does not equal just 2x to the 3rd. So be super careful when distributing those values in. So I'll give you one more, 3 over 2x squared. So try this one out. So pause the video. Distributing it throughout means every single term gets something. 3 squared over 2 squared and x squared. We got 9 over 4x squared. Again, does not equal just 9 over 2x squared. Okay, so just be super mindful of what we are doing as far as your properties go. Now, can you take those properties that we have just learned and kind of rehashed, and can you try out these quick examples here below? Okay, so in the below, right, we have y squared over y to the 7th, which we do have that division, which means we are going to do a subtracting of the exponent. So we should see y to the negative 5th, which when we see your negative exponent, right, something we're not allowed to have, we will then have 1 over y to the 5th. We are changing its location. Now, the reason it came out to be negative is that you only have 2 y's above and 7 below. So then when you canceled 1 for 1, right, you're left with, oops, a little too big, you're left with 5 y's, right? 5 y's on the bottom. So that is how we can also kind of show where the position is. So if you're ever at all confused, you can always just do it like this, where you're just writing your values out. All right, let's take a look at B. Sometimes it helps to look at your what are these called? Your coefficients first. We have 6 up top and a negative 3 below. So 6 divided by a negative 3, that will give us a negative 2. Then we can look at your x values, right? Your x values, we have 2 above and again 2 below. And we can go ahead and cancel 1 for 1. And you're left with just the negative 2. You could also just subtract them. 2 minus 2 is equal to 0. And as we learned, anything to the 0 power is equal to 1. So negative 2 times 1 is just itself. Okay. Talking about anything to raise to the 0 power, all of a sudden we have 1. So this now shoots off to 1 times 5 to the negative 3rd power. So that's an issue. We have a negative in your exponent. So we are going to change the location of it. So we have 1 over 5 to the 3rd, which is 1 over 125. Now in my class, you don't have to know all of your powers. You should know something like this though. I do know that you are not able to have a calculator on the test. So if you're coming out with really, really ridiculously big numbers, there is something wrong. There's usually an easier path. All right, D, we again have a negative exponent. It is in the denominator this time, so we're going to just raise it up. So we just have t to the positive 3. And E, let's go ahead and distribute evenly throughout. And we have parentheses, you have one exponent being raised to another, so we are going to be multiplying those exponents together. And there you have it. So these ones should be quick and easy examples, but now we're going to move on to something that requires a little bit more of us, like we're seeing in example 3. So something a little bit bigger. So for example, something like this. First thing you want to take care of is try to remove any sort of variables, any sort of negatives that we can. So what are you noticing with your 3 chunks? Well, we have negative exponents, which we want to change its location first. That one can come down. We also will do what if anything is raised to 0? Well, this whole thing is really a 1. So what we have left, if we're changing the location of those negative exponents, we have x, y, now raised to a positive 2. We have negative 2x cubed y to the first, or sorry, y to the negative first. The reason why this one is negative is because we haven't changed this location yet. It's really only this negative 3 that has been moved. And that one changes to now a positive 3. You also still have multiplied by 1, so you can represent the 1. You can get rid of it if you want because it is just itself. Now what can we do? Right? Well, we can go ahead and start to distribute values in. Go ahead and distribute. So if we have x squared, y squared over, and keep in mind, this is negative 2 to the third with parentheses. We've seen this one before back on our other page, right? We're just multiplying it out with a pair of parentheses. So we get to keep our negative 8. We have then 3 times 3 to make 9. Y negative 1 times 3 will get us just a negative 3. And let's do that out. I'll put it over here. We have x squared, y squared, negative 8, x to the 9th, and y to the negative 3. So if this is all that you needed, try to pause it and then go from here. Now, one thing you can do is if you didn't want to change the position and if you still wanted to do the quotient rule, you can still say y2 minus a negative 3. That will make it positive as if you were to switch its position, and then you can add them together. Now I'll show you just in case what it looks like over here. If we were to just switch its position, I'll say or y2 minus a negative 3. Now we can go ahead and simplify. So we have y to the 5th above. We have x to the 7th below. Subtracting 2 by 9, you will still get out a negative 7. So then the negative just drops us to the denominator. You have 8. And we still have a negative out front. Now, Hawks will not accept answers with negatives in the denominator. Sometimes they're a little picky about it. Sometimes it goes through, sometimes not at all. So just to be cautious, just put a negative out front of any sort of fractions. If there's multiple things in the multiple terms in the numerator, just use a pair of parentheses just to keep it safe. Okay. Now, why don't you try B and C alone if you have not paused this video yet? All right, so we got a bunch of negatives going on. So we are just going to switch these positions just out of good habits. So we brought z to the 3rd above, z squared alone. We have x cubed remaining. Then we brought x squared, y cubed, and we now have a positive 1. So we still have z cubed. I'm going to just rewrite it without any parentheses and putting just variables next to each other where they would go. Y cubed and z2. And now we can start to combine. You have a z cubed and a z squared. And I'll just do some side work. So you're like, well, where did these values come from? So we have z above, it's positive. We have x2 plus 3 for 5. And y to the 3rd alone. Let's try it again with c. All right, this is the only one that's negative, so this is the only position that gets moved into the denominator. Yes, I am very aware that our z in that first term is has a -2 in it. We're not going to move it quite yet. 5x squared y. And then we can go ahead and distribute throughout. Now, if you wanted to, you can certainly distribute this negative throughout, but keep in mind, if you are distributing a negative, it's the exponent that's negative, it's not the coefficient that's negative. So these would all have a negative exponent, and then you would have to drop all of them because they would all have a negative. So be super careful if you do go ahead and distribute a negative. And I'll put something like that on the side. If distribute negative, then it's 5 to the negative first, x to the -2, y to the -1, not negative coefficients. Okay. So hopefully that answers some of your questions. X squared, z to the -4th, 5x squared, and we have y. Notice that you have an x squared on top as you do below. So we can cancel those out. We can drop that z to the 4th. And there you have it. Now we're going to switch gears and go kind of from those exponents to now radicals. Now we still will talk about radicals in an exponential or an exponent sense, which actually we're going to come into contact with this first one. So if we have a radical notation and we wanted to convert it into a what is this called? An exponential, or so sorry, a base with an exponent. Your base stays the same, so it's just a. And then what's going to happen is that your m is still acting as your numerator. So we still have m on top, but what's making the fraction is really the number n out front. So any value that's found on the outside as a degree of a root, that will be found on the denominator. So let's go ahead and give this quick example a go. So we have x as your base, and then we have 2 divided by, and we have 3 as your exponent, or sorry, as your denominator. You could also, if you wanted to, break this up and just say this is really 2 times a 1/3. You might be seeing that in a moment, but kind of combine those numerators together, you'll still get 2 and 1/3, 2/3. Now, if you have something that already has the same root as it does an exponent, we're going to be using the absolute value sign. Now, you don't need to show it to me for a test or a quiz. I'm just going to be happy either way if you can start to simplify some of these harder values. But just know, if the base of your if the exponent matches the root of the exponent, then they will just have the absolute value symbol. So for example, let's see, do I have one over here? I'm sure I have another example for you. Okay. Now let's take a look at the 2 below. So we have negatives found in the root symbol, right? The radical. Now one of these, right, will contain a non-real solution. Not that it doesn't exist, we're just talking about imaginary here, right? But I'm sure your teachers in the past have said, hey, no negatives under a square root, right? But they're going to be very specific. It's going to be either a square root, a fourth root, or any sort of even root. So no negatives, and I might write that in here. No negative numbers under an even root. The reason for that is that let's just take, for example, the graph of a square root function, which we don't know yet, but we will get very familiar with it. Looks something like this. Well, you're noticing that there are no negative x values provided, right? You'll have different variations of it, and we're going to be seeing that here in our 119 journey, right? But it's graph, plain and simple. It's parent function of just, let's say y is equal to the square root of x, right? Just you are not allowed a negative. Zeros are okay, no negatives. So when it asks you, hey, what are your solutions? You're just going to say non-real solutions. We will be coming into contact with imaginary numbers and imaginary solutions in a little bit. I believe that is going to come up in chapter 3. Yeah, chapter 3. So just leave it as non-real solutions if it's under a square root, a fourth root, a sixth root, any sort of even root. But this one, right, is 3 an even number? No, it's odd. So if we have a value that has an odd solution, or sorry, an odd nth root, then we are able to have a real number. So real solution available. Again, the reason for this is that we're going to be learning here in chapter 3.4 what some of these parent graphs look like. This one will look like this, where you will be able to have negative values in here as well as positive values. So that being said, can you try the remaining of the quick examples? So hopefully pause the video and you're now coming back. So if we have the square root of negative 16, right, we have a negative underneath the square root, which is not okay. So we're just going to write non-real solution. On the other side, we're actually going to see this cubed root of negative 8 is equal to, right? To tackle cubed roots, it's kind of like a square root, where if we were talking about a positive 16, we're looking for pairs of values. So 1 and 16, 2 and 8, and then 4 and 4. 4 and 4 being the pair that we're looking for, right? Pair, we're talking about a square root, 2 of them. If you broke it up as 2 and 8, right? 2 and 4, again, 2 and 2, and then 4 is already a perfect square. So we are finding these two values that are of the same equal measure. So 4 times 4 is 16, right? Same idea comes with a cubed root. What number times itself 3 times gets you to 8? Oops. Well, 8, we can do the same as 1 and 8, 2 and 4, and 4 can be broken up as 2 and 2. Oops, so sorry, I don't know what just happened. So we're looking for 3 of the same number, which is 2. Now keep in mind ours is a negative 8 on the inside, so that negative is going to travel outside with us. We have a negative 2. Now, if those are nice and perfect numbers, perfect cube, a perfect square, then what do we do if we have something like the square root of 12? Well, the square root of 12, we can actually break up a little bit, right, into some of its factors. 1 and 12, 2 and 6, 3 and 4, right? Now, we're under a square root. If you don't see the number, it's going to be a 2. So Do you have a perfect square found within 12? Well, 4 is going to be that perfect square. So that just means we can rewrite this 12 as having a 4 times a 3. They are going to be in its own square roots, and then you can evaluate them separately. So 4 squared is 2, and then the square root of 3, we don't know without a calculator. We can generalize it for sure, but if we wanted the exact answer, we keep it in the square root. So try to break these up into a factor tree and figure out what the biggest perfect square or cube or fourth root is. So let's try these again, just with a little bit bigger of answers. So pause the video when you need to. So if we have the cubed root of x and we want to figure out, can we write it in the exponent or with a fractional exponent, we can say, well, we have the exponent on the inside being a 1 divided by the exponent on the outside, a 3. If we do it again, right, 3, this 3 is actually being multiplied with the square root of 48, right? Well, 48, we're trying to figure out has what as a perfect square. So we can figure out, okay, well, what two numbers add, multiply to 48? We have 1 and 48. You have 2 and 24. You have 3 and 16. You have 4 and, what is that, 12? Yeah, 4 and 12. All right, and we can kind of stop, but looking around, what are your, what is the biggest perfect square? Right, we got 16, which is a perfect square, and 4 is a perfect square, but which one is the biggest one, right? Well, 16 being the biggest one is our better response. We can break this up as the 16 and a 3. The square root of 16 is 4, and this is all through multiplication. So we now just have to multiply 3 times 4, which is 12. Now, if you chose to do the square root of 4 and 12, just keep in mind what we did with the square root of 12, we said was really 4 and 3. And that's where your 16 is coming from, is this pair of 4. And that one. So you just have to break it up a few more times. So one more time. Now 2 to the 10th power, if you don't know what that is or you don't want to do it, right, make it into a fractional exponent. You got this 5 on the outside, so you can do 2 to the 10th divided by 5, which is really 2. So a much better number to evaluate from, 4. Right? A lot of the times we want to convert these into fractional exponents when possible, because we can then go ahead and simplify easily. Now, taking a look at the difference between D and E, one has parentheses and the other doesn't. So if we go to convert from fractional exponents into a radical, which is I think what this question was asking for, right? This radical, this whole thing has parentheses. So that means this whole thing will have a 7th root. And on the inside, a 4th to the 4th. And then if you wanted, I'm sure you can distribute that 9 in, right? You could also rewrite it as being the 7th root of 9x, all being raised to the 4. We want to do this in case it's a little bit easier to do the radical versus the exponent, or vice versa. We said there is a difference with the parentheses, and notice that 9 has what exponent? Well, it has an exponent of 1, so that just gets to stay put, whereas x is the one that's going to be a little trickier. We have the 7th root of x to the 4th. So notice those two big differences, right? With parentheses and without. And if you haven't attempted any on your own, definitely pause here to try this one on your own after talking about D. We have the cubed root of 27x. Now, looking at similarities between what we did in, let's see, part B, where we broke up some of these values, right? We can do the same thing, but with a number and the variable. So we can break it up with its coefficient and see, can it be simplified any further? Well, what is the cubed root of 27? Well, the cubed root of 27, what number times itself 3 times is 27? Well, that number is going to be 3. And the cubed root of x, well, that has to remain because it's not able to be simplified further. Now, those kind of properties that we just talked about in F and let's see, yeah, mostly just F, but we'll talk about here in part 2 and 3, is the breaking up of some of these values. So we just did it where we broke up the 27 away from the x, right? Evaluating this separately. So if they are easily separated or easily evaluated without the additional term, we can just break them up and look at them in terms of a couple mini problems. So let's try to break these up into small problems. So see if you can pause the video and break them up. So you have the cubed root of 3, so you want to separate that coefficient from the variable, times the cubed root of x to the 6 times the cubed root of y squared. So then when we take a look at these values, we're going to be looking at them separately, right? Can we do anything with the cubed root of 3? No, that one has to stay put. But what do we know about 6 and 3 here? And we have that radical exponent, right? Well, let's go from a radical into a fractional exponent. 6 over 3. Well, that's equal to 2. So this one can be easily simplified. When you simplify it, or when you have a whole number that comes out, that is what's going to go on the outside. Doing again with y, we have y2 over 3. Now, unfortunately, this one can't be simplified because 2 over 3, right? 2, your numerator, is smaller than 3, so we can't even make a mixed number. So unfortunately, this one will have to remain as is. So underneath the cubed root will be the 3 and the y squared. We will be talking about what to do if this was something like a 7 or an 8, which I'll just cover here briefly. Let's just say this is y, let's do the cubed root of 7, right? 7 over 3. If we create a mixed number, right, well, how many 3's can fit into this 7? Right, well, this is really 2. And then as a remainder, it's 1/3. To go backwards, you can just multiply these two numbers together and then add 1, right? But that 2 that came out, that really is the value, the exponent that was perfect, right? And then whatever got left behind is going to go back on the inside. So this 1/3 will go in. And we're going to get some practice with that here in a moment. So same idea here as well with 2 and 3. If we can combine them together or separate them together, right? Which one might be easier? So if you notice that they don't divide easily, perhaps we break them up into mini problems. Or we could also go in the reverse. If these two values under the same root, if they are easily divisible, then let's combine them, do the simplification, and then see if there's anything left. So don't be afraid to go back and forth with number 2. So for example, the 4th root of x to the 4th over 16. So if we're looking at these, well, obviously the variable can't really divide by the number. So breaking them up into little mini problems. So separating them out, we have the fourth root of x to the fourth. Notice that they are the same number on the outside as the inside. So we get to use your absolute value of x over, again, oh, and the reason for that, I should really kind of walk you through, right? If we did x to the 4 over 4, we put it into that fractional exponent, it's really coming out as 1 itself. So it needs that absolute value. If we did again with 4th root of 16, what number times itself 4 times gets you to 16? Well, that would be 2. Again, on the test, I'm just going to be happy if you can just give me x over 2. So you can drop the absolute value signs just for me on any sort of assessment. But just on your homework, it's going to be a little picky. Number 3 says m to the nth root times nth root of a. It's hard to say. Notice that what we're going to do, we are going to multiply these two exponents on the outside together to create a mega exponent. So really what is hidden here? Well, this is really a 2. And we just said we get to multiply them together. So this is the 6th root of 64, which I believe in this one is all that you needed to do. But if you do find that it is easier, instead of combining them, but to then separate them out, right? If you don't know what number times itself 6 times gets you to 64, you can think about it in parts. Well, what is the square root of 64? Right? Well, the square root of 64 is 8. And then what is the cubed root of 8? Well, that is 2. So if you don't know how to do a bigger root, bigger root, then just kind of work backwards if needed. So this is our last page. Thank goodness, 4 pages of lecture is a lot for me with a lot of examples. So that being said, can you try out the quick examples, and then we'll talk about rationalizing the denominator. All right, so let's take a look at these little mini problems. So this problem we can break up into little mini problems, separating out the coefficient from your variables. So if we have the square root of 8, well, the square root of 8, right, is not a perfect square, but it does have perfect squares within it, right? We have a 4 times a 2. So we can take the square root of 4 and the square root of 2, which comes out to be 2 root 2. And we are multiplying everything together. So whatever comes out following, we're going to multiply. So then we have x squared, right? And if we're working with a square root, dividing by our 2, your root, will get us equal to 1. So the absolute value of x, because they have the same exact value. Okay. And one more. Y to the 4th divided by 2 is equal to 2. So we now have y squared. So putting it all together, because I would hate if you left your answer like this after all that work, we have 2 times the absolute value of x times y squared with the square root of 2. Let's try it again. All right, 3 times, the cubed root of 27, the cubed root of x to the 7th, and the cubed root of y to the 9th. So again, evaluating them separately. This one is already a perfect square, 3 times 9, 3 times 3. So we got 3 of these 3's. X to the 7 over 3, let's make that a mixed number. So how many 3's can go into 7? Well, you have 2 of them to make 6, and then you need 1 more to make 7. So that 2 is really the exponent of your x value that came out, and the 1/3 is really what stays back inside. And lastly, y to the 9th over 3, which is equal to 3. So you have y to the 3rd. Oops. 3 is, and there you have it. All right, let's try it again with these values. We have the square root of 15 over the square root of 5. Now, are either one of these perfect squares? No, but what do you recognize about 15 and 5? Well, they can kind of divide by 1, or 5 can divide 15 pretty easily. So if we create it so that they are now under the same root and easily divide them, we're left with the square root of 3. So while we then have to stop, right, the square root of 3, we can't go any further. This is as simplified as it gets. So if we can recognize that the values within it can divide a little bit easier than evaluating them separately, definitely break them up. All right, the opposite is true on this one. 16 and 9 can't divide easily. So instead, let's break it up, see if we can evaluate them separately. Well, the square root of 16 is 4, and the square root of 9 is 3. And there you go. Now, something that does come with radicals is going to be rationalizing the denominator. So with rationalizing, you're going to be seeing this coming up in chapter 7, where we see lots of square roots in the bottom with our unit circle. So over here, we have 4 over the square root of 8. So when we go to rationalize, it's asking us to simplify the denominator. We do this by multiplying the denominator by itself. So if we multiply the 8 by itself, this will in turn, what you do to the bottom, you do to the top. In turn, you have the square root of 8 times 8, which equals the square root of 64, which is equal to 8, right? Multiplying by itself is easy because it just gives you a perfect square automatically. You could also, if you wanted to, say the square root of 8 is really the square root of 4 times the square root of 2, and say 2 root 2, and then throw it back into the problem and simplify it a little bit before getting started. So you have 2 over the square root of 2. So that's one way, but it's still leaving you with the square root in the bottom, in which case you would have to still rationalize to get it out of there. You could also say, instead of multiplying by an 8, you could multiply by a 2 to make it 16, to then get you a 4, and then multiply up here, right? So lots and lots and lots of different ways to tackle this one. I just say, make it easier on yourself. Maybe you have to simplify a little bit later. Just multiply by itself to get you a perfect square. So 4 square root of 8 over 8. And then you'll notice 4 over 8 can reduce to 2 on the bottom. And then what did we just talk about? The square root of 8. We can combine as 2 root 2 and then simplify over 2. So lots and lots and lots of different ways. If you didn't like that way, maybe it was a little too much simplifying for you. Instead, maybe you wanted to do this path, in which case you would end up with 2 root 2 over, again, just by multiplying by itself, it's just this number 2 on the bottom, 2. Or you just get to the next biggest value by multiply by, in our case, if you wanted to do the square root of 16, super easy. So let's try it again. Just try multiplying the denominator by itself on b. So multiplying it by itself, we get 3a, or the square root of 3a up top. And on the bottom, again, I'll kind of show you the behind the scenes. We have 3 times 3, a times a, so square root of 9a squared, square root of 9, square root of a squared, so 3. And you can do the absolute value of a, it's not necessary here. But otherwise, we're just going to say 3a. And there you go. We cannot cancel them out. One has a square root sign, so we have to leave it as is. Let's try it again over here. Now this one is a little bit different because we have an addition sign. Now what we're going to do is actually multiply by the complex conjugate. The complex conjugate is down below. Is really the difference of squares. So to get out your square root, right? We don't want the square root to happen. So to get it out, or get it just to get it away, right? We're going to multiply by the opposite sign. That way, when we go to multiply it through, these square roots end up canceling with each other. What you do to one, you do to the other. Square root of x minus 5. So then you have x times the square root of x minus 5 above. And below, on the bottom with foiling practice, we have the square root of x plus 5 times the square root of x plus or minus 5. Now this is going to be nice because when you go to do your foiling, right, your first two terms is really the square root of x all squared, plus your next two is a negative 5 times a square root of x. And your next two is now a positive 5 times your square root of x, which you'll notice these two will end up canceling with each other. And then you have your last one, plus 5 times a negative 5. So those middle terms are going to cancel. You get a negative 25 over on one side, and on the other, because they're square roots, right? Think about 2 over 2, which is 1. Again, absolute value sign isn't necessary here. It's just an x. So over here, we have x times x minus 5. So sorry, the square root of x minus 5, then x minus 25. Now, do not be tempted to cancel out these x values. We'll talk about this in chapter 1.4 when we can cancel. Simple answer is that you need a pair of parentheses when canceling out terms with an addition and subtraction sign. Okay. So last thing we are going to do is combining rational expressions. So we just learned how to simplify all the way through, and now let's, and we actually just multiplied. So now let's do adding and subtracting. So as you're going through, think about these square root signs as being variables. So combining your like terms, as long as they are the exact same, we can go ahead and add them together. So 4 plus 7 is going to be 11, and then your quote unquote variable, 3x. Now what happens if they are not exactly the same, right? Then you kind of have to evaluate, well, I have an 8 here and I have a 2 here. Those kind of contain some similarities. We also have an x on the inside and another x on the inside. So let's just see if we can make this into a 2x to see if we can then further combine your like terms. So if we went ahead and use what we've learned from before, kind of breaking them up, we would get negative 2 root 2, right? This is all the way from knowing that the square root of 8 is really the square root of 4 and the square root of 2 times, and then x to the 5th over 2. Well, how many 2's can fit into 5? Well, that would be 2 pair of 2's, and then the 1 extra remaining to make the 5. So this was really x squared and the square root of x. The square root being this one, and the 2 being that one. So bringing them back together, you have negative 2x squared times the square root of 2x. Bring this whole thing down, minus 6x squared, square root of 2x. Now, are your square roots the exact same? Yes, they are. We also take a look at what's on the outside. Again, these are still the exact same. Your coefficients are different, that's okay. But these variables are still the exact same as well. So just like any sort of combining your like terms, they have to look exactly the same with the variables. All right, one more for B. Oh, I'm so sorry, this should be C. All right, now if you did not pause it yet, please try and pause it with part C and see what you can come up with. All right, 16b to the 4th, we want to see, well, they do kind of have similarities between 16 and 2. We do have a b and a b over here, so let's see what we figure out. So the cubed root of 16 and the cubed root of b to the 4th. Well, let's see, 16 we know can be broken up, and we're looking at cubes, so perhaps we do the cubed root of 8 and the cubed root of 2, right? 2 and 8 make 16. So you have 2 root 2, or the cubed root of 2, and b to the 4 over 3. How many 3's can make up a 4? 1 and a leftover. So b and the cubed root of b. So bringing it all together, we have 2b with the cubed root of 2b plus 5b cubed root of 2b. They are the exact same over here. They are also the same here. So we can go ahead and combine for 7b cubed root of 2b. I'm again just going to highlight one more time. Let's see, over here. There you have it. So hopefully that answers all of your questions with rationalizing, combining, any sort of properties you have for this video.